In this lesson, we're going to be looking at the area between curves. How could we find the volume of the following figures? Here we have a pyramid. Now, in pre-calculus, we learned a formula to find the area of a pyramid. So we could just apply that formula. But what about an irregular shaped object? Here we have a donut. We really don't know of a formula for the volume of a donut or a football. Or how about something like a liver, human liver? We don't know how to find the volume. We don't have an explicit formula to give us the volume of these different objects. So we're going to learn how can we find the volume of some irregular shaped objects using calculus. That's what this section is about. Now, to get us started, we're going to look at finding the area between two curves. So take a look at these two curves, and let's say we want to find the area between these two curves here. We could find the area underneath the curve of f of x down to the x-axis. That would be the area under f of x. And then we could find the area under the curve of g of x, which is indicated by the blue lines. Now we see that if we were to take the area under the curve of f of x and subtract off, so if we subtracted off this area right in here now, if we subtract that off, we would just be left with the area under the curve between the curves of f of x and g of x. That would give us this area right here. So that's how we could find the area between two curves in general. Now, does the area between the two curves change if one of the curves is below the x-axis? In the previous slide, we had both functions were above the x-axis and we just subtracted g of x from our f of x. Let's try to analyze this one a little bit, see what happens. Say we're trying to find the area between the two curves here, and our g of x this time is below the x-axis. Now, if we look at the area between the two curves, we have this area here. And if we looked at finding the area under our f of x, let's label the top curve f of x. So this is y equals f of x. And let's say this is our curve y equals g of x. If we find the area under the curve of just f of x, we would be finding this area right in here. So that would give us the area under the curve of f of x. Now, let's represent that as the area under the curve of f of x. Looking at the curve g of x, if we looked at calculating the area under this curve, we notice it's below the x-axis, so it's going to give us a negative area. So what actually happens is we're going to be adding these two areas together. So just because the g of x graph, the graph of g of x, is underneath the x-axis, it still does not change the way we would find the area between the two curves. Now, what if both of the curves were underneath the x-axis? Let's say our curves were, let me just draw two curves in here. let's say this is my f of x, and here we have some g of x, where both of them are below the x-axis. And we're trying to find the area between these two curves, let's say. Now, if we found the area for f of x, we would be finding this area right in here, which would be a negative area. So we are finding this area right in here. That would give us a negative area. And then if we found the area under the curve of g of x, that would also give us this negative area here. So we would be finding this total area here. So we would have minus a negative area for g of x. Now notice the area for the curve of g of x is a larger negative area than f of x. So for this quantity here, this would be a plus a sub g of x. And that would give us a positive area for this whole piece right here. That would be positive. And then we're going to subtract off this piece right here, which would leave the area between the two curves. And the reason we'd be subtracting this area off is because we have this negative area. So that shows that it does not matter where the curves are situated. One could be above the x-axis, one below, both of them above, both of them below. We're still going to take the top curve minus the bottom curve to calculate the area between the two curves. So looking at the area between the two curves, if we found the area of the rectangles, you can see the area under our f of x will give us a positive area. Then we would subtract off the negative for g of x, and that would give us the total area of this rectangle. Now we are going to look at this through a Riemann sum, and we're using the midpoint of the rectangle. So here, the total length of this rectangle would just be f of x sub I minus g of x sub I. And then if we found all of the rectangles to estimate the area between the two curves on the interval a to b, it would look like this. Now to find the area between the two curves, we could take the limit of the summation of f of x sub I minus g of x sub I times our delta x, just like we've been finding the area under a curve. We know this is the definition for an integral. So we could write that as the integral of f of x minus g of x dx. So there's our rule for finding area between two curves. Let's try an example. Find the area of the region bounded above by y equals x e to the x, bounded below by y equals x, and bounded on the sides by x equals 0, x equals 1. Let's draw a graphical representation of what's happening here. So we would have, here's our interval, and there's the two graphs on the interval, and I have drawn a representative rectangle. Now to find the area between these two curves, we said we're going to take the integral on the interval from 0 to 1 of our top function. E to the x is going to be our top function. So that would be e to the x minus our bottom function. So this will calculate the area between the two curves. Now the reason I like to draw in this representative rectangle, this is going to come in very handy when we start looking at volumes of revolutions. Here, with this rectangle, the width of the rectangle would be delta x, and then the height would be our f of x sub I minus our g of x sub I. We can see that we're in functions of x. Now in some problems we could rotate that rectangle and the widths would be delta y instead, so we would have to have functions of y. So it's very important to understand if you're going to be working as a function of x or a function of y. So I highly recommend that we draw in this representative rectangle to get it started, because that tells us the width of each rectangle is delta x, and so our functions need to be functions of x, not of y. These upper and lower limits of integration then have to be as a function of x, where we're going on that interval. So we're going from here, x equals 0, to x equals 1. Now if we were doing this in terms of y, we'd be going from y equals 0 to y equals something up here. So you can see those limits of integration would change if we were doing it in terms of y. All right, so let's finish this problem. Now the antiderivative of e to the x is e to the x minus, then antiderivative of x is x squared divided by 2. We're going to evaluate this on the interval 0 to 1. So we would have e to the 1 minus 1 squared over 2 minus e to the 0 minus 0 squared over 2. So we have e minus 1/2 minus 1, because here we do get e to the 0 is 1, so we have minus 1. So we get e minus 3/2. And that would be whatever the units are, if they are inches, centimeters, yards, miles, whatever, units squared, because we're finding area. So we'd have e minus 3/2 units squared. And there's a graph of what the area that we just found. The graph of e to the x, y equals x, and the area between the two curves on the interval 0 to 1. Find the area of the region enclosed by the parabolas y equals x squared and 2x minus x squared. Now with this problem, it doesn't give us where those graphs intersect, or the interval where we're trying to find the area between the two curves, but it does say find the area that's enclosed by them. So we know it's at those points of intersection, because if we looked at the graphs, these would continue down this way, this one, and this is not enclosed by the graphs. Likewise, on this side over here, this area is not going to be enclosed by the graph. So we're only looking for from, it looks like x equals 0 to, well, we think it's x equals 1, but let's be sure. Let's set our equations equivalent to one another and see where they intersect. So if we added x squared to both sides, subtracted 2x, factored out a 2x, we do get x equals 0, x equals 1 for our points of intersection. Now we can build our integral. So we would have from 0 to 1. Now our f of x, I'm going to consider this our f of x, our top curve. And then the g of x, the blue curve, would be our bottom curve. Well, how do we know which one is f of x and which one is g of x? Well, looks like the green, the f of x, would be an upside down parabola. And so we would have 2x minus x squared as our top function. So if we draw in our representative rectangle, we can see the width of this rectangle would be delta x. So we're going to be working in functions of x. So our top function, we said, is 2x minus x squared. And then we're going to subtract the bottom function on that interval, which would be x squared. So that's how we set up our integral to find the area between the two curves. Now if we simplified this, we get negative 2x squared dx. And if we find the antiderivative, we get x squared. We would get x squared over 2, so I'm reducing the 2's, minus 2x cubed over 3, evaluated from 0 to 1. So we have 1 squared minus 2 times 1 cubed over 3. Now we're going to evaluate at 0. So we'd plug in 0, and we would get this. And that quantity goes to 0. So we're left with 1 minus 2/3, which is 1/3. And whatever our units would be, we would square them. So we have 1 minus 2/3 gives us our area between the two curves. Find the approximate area of the region bounded by these two curves. Okay, let's again draw a graph to represent these two curves and the area that or the region we're trying to find the area between these two curves. And I have already gone ahead and zoomed in on that area that we're going to find. And we can see the points of intersection. Now with your graph, you would see more of the graph, and you would see this is the place where these two are enclosing this area. So we need to find the points of intersection. Now this one we're going to do graphically with our calculator, and we'll use our trace feature to find those points of intersection. So if you use your calculator, graph in y sub 1, graph your first function, and then in y sub 2, graph your second function. You would see that this is the top function and this is the bottom function. And when you used your trace feature, you would see that this point of intersection occurs approximately at 1.18. So that's the value we're going to use, and this point of intersection you would find is x equals 0. So those are the points we're going to use for our integral. So we would have the integral from 0 to 1.18. The top curve is x divided by the square root of x squared plus 1. Let me write that in for the entire integral. Minus x to the fourth minus x dx. Now finding the antiderivative of our first term, we would let u equal x squared plus 1, du would equal 2x dx, and we can see in the integrand we don't need the 2. So this integral would become 1/2 the integral, our x dx is replaced by du over 2. So we'd have this 1 over the square root of u, which is u to the negative 1/2. Now if we take the antiderivative, we would add 1, so add 2 over 2. So we would get 2u to the 1/2, and our u is x squared plus 1. And now we're back into terms of x. So let's complete our integral and our evaluation of the integral. Let's reduce these 2's. So we would have x squared plus 1 to the 1/2 minus, now this would be x to the 5th over 5, and then plus x squared over 2 from 0 to 1.18. So applying the fundamental theorem, we would plug in 1.18 squared plus 1 to the 1/2 power minus 1.18 to the 5th divided by 5 plus 1.18 squared divided by 2. And then we would subtract off, now we have to plug in 0. So we would get 0 squared plus 1 to the 1/2 minus 0 to the 5th over 5 plus 0 squared over 2. Plugging this into your calculator and finding this decimal approximation, this is approximately 0.785, and that would be units squared. So that's the area between the two curves. The graph below shows velocity curves for two cars, A and B, that start side by side and move along the same road. What does the area between the two curves represent? Use the midpoint rule to estimate. If these curves are represented by velocity, or this is our velocity function, the area under the curve of A would be the distance car A has traveled. The area under the curve for B would be the distance car B has traveled. So if we find the area between the two curves, that should represent the distance between the two cars. Now it says use the midpoint rule to estimate. And if you had 4 rectangles, if we are looking at the area from 0 to 16, and we would have 16 minus 0 all over, we have 4 rectangles, so the width of each rectangle would be 4. We would find the area under the curve for this graph, for A. That would be our estimate for the area under the curve. And so for car A, the width is 4, and then the height we're going to have to approximate. I would say approximately 38. Then we could find the area under the curve for car B and subtract that off. So for car B, the width of our rectangle is still 4, but there we have a height of approximately 22. So that would give us, if we subtracted these two, A minus B, we would get the estimate for the area between the two curves. And then you would just do this for, same thing for this one. We would have, and if you wanted to find the area under the curve for A and then subtract out B, you could do it separately like that also. Here it appears that the height of this one is 50. Now for car B, we would look for the area of this curve, under this curve. So the width is 4, and the height, it's around 36, let's say. Finding the area under the curve here, we know we'd have 4 times, and let's say that's a height of 55. And then for this curve, we have 4 times 39. And then the last rectangle, we have 4 times 60. And then B is 4 times 40. So that's using the right side of the rectangle. And I just noticed that we did indicate on this problem we were to use the midpoint rule. So this calculation that we just did would be for the right side of the rectangle. And let's just set up what the midpoint so this would be the right side of the rectangle. So down here, let's just set it up. If we did use the midpoint, how would it look different? Now if we're going to use the midpoint, we still have a width of 4, but now we're going to use the midpoint. So the height of this rectangle, 1, for this function, again this is for area under the curve of A, we would still have a width of 4, but the height would be 22. Now for rectangle B, I'm going to find the midpoint at 2, and then I draw the height of the rectangle at that point. So this is the area we're subtracting off. So that has a width of 4, and then the height is 12. Second rectangle goes out to 8, but we want the midpoint. That's right here. So we would have this rectangle is our large rectangle. So plus the width is 4, but then the height is 43. But for the area under the curve of B, we'd go to the midpoint, and that would give us 31. So this is how we would set it up for the midpoint. So here we're going out to 12, but we want the midpoint. So we would have 4 times 52, and then here we would have this rectangle now. We're going to end up subtracting that off. So that would be 4 times 38. And then the last, we would have 4, and here's the midpoint, so that would be our rectangle for the top function, 4 times 59. And then the bottom, we would have 4 times 40. So if we calculated this off, we would calculate the total here for the area under the curve of A, calculate the total area under the curve of B, and we would subtract them off. And we would get something around 370 or 372, around that area. And your estimate could be a little bit different than mine, just depending on the values you chose. We had to estimate these values. So you could have estimated this one may have been 42 instead of 43, or something like that. But this is approximate area then. Find the area of the region bounded by the curves of sine of x and cosine of x on the interval 0 to pi by 2. Here's our graphical representation, and we know that pi by 2 is about 1.57, so right in there we're trying to find the area between the two curves from 0 to here. Now, to pi by 2. Now we can see the area between the two curves here and the area between the two curves here. Okay, that area in the middle is not enclosed by the two curves. Notice on this graph from 0 to pi by 4, the top curve is the cosine curve. But on the interval pi by 4 to pi by 2, the sine graph is the top curve. So we're going to have to build two integrals to catch both of those areas. The first one would be from 0 to pi by 4, and the top curve is cosine of x. And then we would subtract off our sine of x. And then the second area is going to be captured by adding on the integral from pi by 4 to pi by 2. Now the top curve on this interval is sine x, bottom curve cosine of x. The antiderivative of cosine is sine of x. Now minus the antiderivative of sine of x is negative cosine of x. We're going to evaluate that from 0 to pi by 4. Then plus antiderivative of sine of x, negative cosine of x, minus the antiderivative of cosine, which is just sine of x. And we're going to evaluate that from pi by 4 to pi by 2. So if our curves switch, we need to represent the areas with two different integrals. So here we would have sine of pi by 4 plus the cosine of pi by 4. I made these into a plus. So then we would have minus sine of 0 plus cosine of 0. And then we would add on, I don't know if I can fit this in here, add on, we would have negative cosine of pi by 2 minus sine of pi by 2 minus negative cosine let me write that down here, minus then we would have our cosine. Yeah, I'm going to have to move this. Let's write this below so we don't make any errors on this. So we would have plus and then minus cosine of pi over 2 minus pi cosine minus the sine of pi over 2 minus a negative cosine of pi over 4 minus sine of pi over 4. Sine of pi over 4, square root of 2 over 2, plus square root of 2 over 2, that's cosine of pi by 4, minus sine of 0 is just 0, and then the cosine of 0 is 1, but we have to distribute that negative, plus, now we have negative cosine of pi by 2, which is 0, minus sine of pi by 2, and then we have minus, I'm going to change this to a plus, this would be square root of 2 over 2, and then distributing the plus here, square root of 2 over 2. Here we have 1, 2, 3, 4 square roots of 2 over 2 minus 2, which would give us 2 square roots of 2 minus 2 units squared, whatever the units may be. I spoke earlier about being able to find the area between two curves with the rectangle when the rectangle is horizontal instead of vertical. Now the idea here is our width of this rectangle is going to be now delta y. Therefore, we're going to have this function as a function of y, subtracting off this function as a function of y. And then we're going to be looking at, instead of x going from a to b, we're going to be looking at the y values going from c to d. Let's try a problem where we would have horizontal rectangles instead of our vertical rectangles. Find the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. Now the parabola y squared equals 2x plus 6 is a sideways parabola, as we can see here. If we wanted to find the area between the two curves this way, where we would have delta x, we would be okay up to this point because the rectangle is touching two different functions. But when we got it back into this area, we would be subtracting the same function from itself, so that would give us a problem. That's why we're going to set the rectangles up in a horizontal direction instead of a vertical direction. We are going to have a width of delta y. So that right there tells us we have to have a function of y for each one of these. So we have y equals x minus 1. So a function of y means I'm going to solve for x instead of y. So I would have x equals y plus 1. And for this one, if I solve for x, we have y squared equals 2x plus 6. So I would subtract 6 and divide by 2, and that would equal my x. And then we're going to be going from x equals negative 2 all the way up here to where it intersects at y. I put x, that should be y. So let's rewrite that as this should be y equals 2. Y equals negative 2 all the way up to y equals 4. So our integral would be from negative 2 to 4. Now, we're not looking at this in terms of x, so the blue function is not our top function necessarily now. We want to find values of y, look at the function. For, let's say, this value right here, close to y equals 2. Which value of x has the greater value? Here, this function has a value of maybe 3.2, where this function has a value of negative 0.25. So this would be considered the top function, the red graph, because we're looking for, just think about if we had a function in terms of x, we're going this way with our rectangle. So we're looking for for any x value, the y value here is greater than the y value for this graph. The y value here greater than the y value. This time we're looking at the x values. This x value is greater than this x value for this y value. So our top graph would be our line, which we said is x equals y plus 1. So that would be our top function minus our bottom function. And when we solved for our bottom function, we had y squared minus 6 all over 2. Finding the antiderivative of y is y squared plus antiderivative y. It's y squared over 2. This one, if we think about this, is y squared over 2 minus 6 over 2. We would have minus y cubed all over 6. And then plus, this would just be 3. So it would be 3y, evaluated from negative 2 to 4. Now we can apply the fundamental theorem. Applying the fundamental theorem, we would have 4 squared divided by 2 plus 4 minus 4 cubed divided by 6 plus 3 times 4 minus. Now we're going to plug in negative 2. Negative 2 squared over 2 plus a negative 2 minus a negative 2 cubed over 6 plus 3 times a negative 2. And if you calculated this, we would get 18 squared units. So there's the area between the two curves, and the area, let me just outline the area that we just found. We found all of this area in here between the two curves, this area here.